Good evening, everyone. Am I audible? Please someone confirm if I'm audible.
Yes, sir.
Okay, fine. So maybe we'll do a very quick recap of the week one, and then we'll start solving the assignment problems related to week two. Uh, so welcome to the live session for week two for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving similar assignment problems from the topic of week two that will help you in solving the assignment problems that is given to you in the week two assignments this time. So this is the course outline that we had discussed in the last week also. So the week one consisted of very simple topics such as semiconductor devices, very basic in daily life. Then we read some of the energy levels, how do they come, and then some of the questions from Schrodinger's and band gap, etc. Now this week we'll be covering about some of the carrier properties. That is, if we have some semiconductor, what can be the properties, what is Fermi level, what are impurities that can be added into a semiconductor which is pure. Then we'll see what are the Fermi levels that will change in the intrinsic semiconductors. And similarly, there are various topics that we will be covering in this week. So for now, if you have any doubts from the previous week, you can ask. Otherwise, we can start from directly from week two. So you can quickly let me know in the chat box if you have any doubts. Otherwise, we'll start for this week. So I'll wait for a minute or so, and then we'll start for the problems for week two. Okay, so fine. I assume that you don't have any doubt from week one. So if I give you a very quick recap, so what we did in week one is, hello, did someone say something? Okay, fine. So we took a very basic idea for Schrodinger equation for a 1D potential well, that is a infinite potential well in which we have a zero potential and an infinite potential elsewhere. And from this, we get to know that the energy is quantized. So this was a basic idea that we get from the week one lecture, and we know that for a infinite potential well, what we have is we have the discretization of energy, which is given out by this formula, which is nothing but, or I can write this as n square h square by not 2 8 ml square, which shows that energy is discretized with the value of as a ratio of n square. And we also solved similar problems in which we were calculating the ratio of energies if a electron is orbiting from some particular energy level to the ground state. So here we get to know that the energy is quantized, and why even we read about this quantum mechanics is because using this only we will be solving for the density of states. So this is the topic that might have been covered in the theoretical lecture itself. So what is density of states? It is basically the number of states that is present per unit energy per unit volume in a semiconductor. So the basic motivation to study first of all the Schrodinger is to get the idea of the quantization of energy, and we basically solve the Schrodinger equation. So the solution of Schrodinger equation basically gives you the density of states. So the derivation has already might have been covered in the lecture, so I'll not cover the derivation, but to get the very basic idea, what we get to know that the density of states is a function of energy as a square root for 3D semiconductor. If we solve the 3D Schrodinger equation, then this is what we get. So once we have the density of states, we already read about the Heisenberg uncertainty principle also in the first week, which gave us the idea that we don't know about the certainty of position and momentum altogether. So that is why what we do is in semiconductor physics, we calculate the probability of electron because we don't know the exact value of if there is any electron present at a particular region or not. So what we do is we calculate the probability of the electron, which is defined by a function known as Fermi-Dirac distribution function. Which is basically given out by Fe is 1 over 1 plus exponential of E minus Ef over kT. So where Ef is a Fermi level, kT is just the Boltzmann's constant divided by multiplied by the temperature. So it is also known as at room temperature we have kT by Q, that is in electron volts, as 25 milli electron volts. You already might have read about the same. So yeah, this is what we have. If I talk about the very basic of the Fermi distribution function and the density of states, from this we calculate all the carrier concentration, etc. So we'll now dive into some of the problems that we have, similar problems. So as you can see, the problem states that consider an intrinsic silicon. So can anyone tell what is intrinsic? Very quickly, if someone can tell. Any idea? Anyone? Okay, so basically intrinsic semiconductors are pure semiconductors. That is, there is no impurity present in the semiconductor. That is, they are charge neutral. We have a classification of semiconductors as intrinsic and extrinsic. That is, we already know. So intrinsic semiconductors are the pure semiconductors, whereas extrinsic have some kind of doping, which are further divided into p type and n type. So we'll see about this later. But in this particular case, we have a pure silicon, which has a band gap of 1.12 electron volts that we all know, and the temperature is at room temperature. So now the question says, let the probability that the state located at the bottom of conduction band. So if I draw a pure conduction, a band diagram for a intrinsic semiconductor. So what we have is, we have a conduction band, we have a valence band, and we have an intrinsic energy level. So can anyone tell where will be the Fermi level for a intrinsic semiconductor? Anyone? Does anyone have any idea? Okay, fine. So for an intrinsic semiconductor, what we have is a Fermi level is at the in between of the conduction band and the valence band. So basically, EF is located at EC plus EV by 2. That is in the middle of the conduction and valence band. So that is what the question says. We have an intrinsic silicon and the probability of the state located at the bottom of the conduction band. So the probability is given out by this function that we already discussed, Fe. So Fe basically is a Fermi Dirac distribution function. Maybe I can write that also. So what is does is Fe gives out the probability of finding an electron at energy level E, that is given here, E, at temperature T. Then similarly 1 minus Fe, since it is a probability, so it will be 1 if there is an electron. So 1 minus Fe gives the probability of finding a hole at again energy E at temperature T. So I hope you already are aware of what are electrons and holes. So holes is nothing but the vacancies that are created uh, when a, so let's say this is the valence band. So when a atom travels from conduction band, sorry, from valence band to conduction band, let's say a electron travels here. So what it does, it creates a vacancy. These are the holes that we have, and these are the electrons. So probability of finding an electron at energy E is given out by Fe, and 1 minus of that will give out the probability of finding holes. Now the question states that the probability that the state located at the bottom of conduction band is filled is Fc. So Fc is here. So at the bottom of conduction band we are here. So the probability is given out by Fc, which is given in the question at the bottom of conduction band. So what we will keep the energy as EC, because the energy at the bottom of conduction band is EC. So is there any doubt in this particular expression how Fc has come? Please let me know if you have any doubts.
No, sir.
Okay. So now if we read the question further, then it says the probability that the state located at the top of valence band is empty is Fv. So now the empty states, first of all, we'll calculate the probability of empty states from 1 minus Fe. The in general formula, that is 1 upon 1 plus exponential, sorry, so that will be 1 minus Fe, because now the question is saying the probability of empty states is what. So I'm just calculating it. So if I take the LCM of this, it will be 1 upon 1 plus exponential E minus EF over KT, and I'll have 1 plus exponential the same term and minus 1, which will get cancelled, and 1 minus Fe will be given out. So if I take this numerator into the denominator, like divide the both numerator and denominator by the term in the numerator, so what I'll get is 1 upon 1 plus exponential of minus E minus EF over KT. That will give me 1 upon 1 plus exponential EF minus E over KT. So this is the probability of being empty. So this is what is given in the question as Fv, and it is given at, so you cannot say this is Fv. So what we can say is for empty we can use this formula, and it is given that it is at the bottom of the valence band. So I'll use the energy as Ev here. So this is the second equation that we have got, and what we had is we had the first equation as this. Is there any doubt in both of these equations? Please let me know if there are any doubts.
No, sir.
Okay. So let me rewrite quickly both the equations that we have got. What we have got is Fc is 1 upon 1 plus exponential Ec minus Ef over Kt. Fv is 1 upon 1 plus exponential F minus EV over KT. So now you can see in this particular equation, the term that we have in the exponential is EC minus EF. And the term in the exponential in this equation is EF minus EV. So if I again make the band diagram very quickly, so this is what we have, EC, this is EV, and the Fermi level is in the middle, that is EF. And we also have that EI, which is denoted by this yellow color. So what you can see here is this EC minus EF. So this is EC minus EF, right? And this is EF minus EV. So can we say that EC minus EF is equals to EF minus EV, that we already know that it is in the middle, from where we get that EF is nothing but EC plus EV by 2. Do you understand this?
Yes, sir.
So if this EC minus EF is equals to EF minus EV, so what we can write simply is the probability that the conduction band bottom is filled will be equals to the probability that the valence band will be empty. So the answer to this question will be FC is equals to FP, which is option B. So I hope the question is clear. It was very simple. Just it is trying to just cover your basics, and you should have a good idea on how the electrons and holes are being generated and what is the probability there. So you can just take a look, and we shall go to the next problem in 1 minute. And if you have any doubt, you can ask in the chat box. Okay, so let's proceed ahead. So what we have read is Fe is 1 upon 1 plus exponential E minus EF over KT. So let's do a very quick analysis on how this Fe changes with your energy. That is very important to go further. So what we know that at, if I take the case when t is not equals to 0, in this denominator t is not equals to 0. So at t is not equals to 0, so if I say that at energy is equals to EF, what we'll get is Fe will be 1 upon 1 plus exponential EF minus EF, so that will be 0 over KT. So that will give me 1 over 1 plus 1, that will be 1 by 2, which is 0.5. So what it states it that at, in any band diagram, whenever the energy level is equals to the Fermi level, that is, let's say this is EF, the probability of electron on that particular Fermi level, that the probability that there will be an electron there will be always half. This is what it says for t not equals to 0. And if I say at t is equals to 0 Kelvin, now there can be two cases, either E will be greater than EF or E will be less than EF. So if, let's say, I'll say if E is greater than EF, so what I can write is Fe will be 1 upon 1 plus exponential. So first of all, I'll have a 0 in the denominator, and E is greater than EF. So this particular term will be positive. Positive something over 0 will be plus infinity. So what I can write is 1 over 1 plus positive infinity. that will be 0 because we have a very large value in the denominator. And similarly, if I say E is less than EF, so this Fe will be 1 upon 1 plus exponential of minus infinity, which will make it 1. That is the maximum probability. So this value will be very low, that is almost equals to 0. So what we have just got to know is if I plot Fe as a function of energy. So at EF point, that is, let's say here is EF. So at EF, I have the probability of having any electron is 0.5. Say which is here. So there will be a sharp transition. Then when E is less than EF, so this will be the part when E is less than EF, we always have a probability that there will be an electron, and when E is greater than EF, sorry, then we always have the probability that the electron is not there. So we have a 0 here. This will be the plot. So this is just to give you some insights. So now what will happen? This is very easy to calculate. So let's say when E is less than EF and we starts to increase the temperature, that is in the equation only. So what will happen? This probability will starts to decrease, and this probability will starts to increase, because as we increase the temperature, there will be some probability that the electrons will be there in the conduction band, like it will go over the Fermi level. So if I can write EC, EV and EF. So if I increase the temperature, so there is a possibility that these electrons get excited and go over the Fermi levels. So more the temperature, more will be the probability. So if I can draw maybe, so let's say this is for a temperature T1, the purple one. So if I increase the temperature, let's say even more, so what will I have is, I'll have, sorry, I'll have even, okay, sorry. Uh, so let's say this is T2. So does it make sense? Any doubts in this particular thing? If we increase the temperature, we will have a difference in the probability. So what we can say here, that this brown thing is T2 and this purple temperature is T1. So higher the temperature, so T2 will be greater than T1. So higher the temperature, we will have a more and more probability that the electrons will flow from this valence band to the conduction band. That is what we always get. Does it make sense to everyone? Any doubts? Please quickly let me know if you have any doubts. Otherwise, we can solve a problem on this.
Hello, sir.
Yeah.
T2 greater than T1, then the probability increase.
Okay. So you need to see that we have energy level like that. So this is EF, this particular line. So if the energy is lesser than EF, so we are in the here, and wherever the energy is greater than EF, so we are here. So the probability is increasing for this part, that the electron will be there. So as we increase the temperature, we have a more probability that the electron will go towards the conduction band.
Okay, sir.
Yeah. So let me frame a question very quickly. You all guys should try to do it. So let's say I give you that the Fermi level. So I'll give you 5 minutes to solve this problem. So you need to do it quickly. Let's say Fermi level I give you for a semiconductor is let's say 5.5 electron volts, and it follows the Fermi distribution function. So I'm just writing it as it follows the FE function. So what you need to find out is you need to determine the temperature at which there is a probability of 2% that the state 0.25 electron volts below the Fermi level will be empty. You need to focus this that I am asking about the probability that it will be empty, not filled. So this is the question. So what is the question? You need to determine the temperature. What I've given you, I have already given you the Fermi level. I've already given you the change in the state, that is how it is. It is 0.25 below the Fermi level. So it is something, let's say this is the energy. So this is 0.25 below the Fermi level. And the probability that it is uh, empty is 2%. So you need to find the temperature. You have everything. It will be solved using again the Fermi Dirac formula only, which I'll write here for your ease. Yeah, this is the problem. So you can take 5 minutes and let me know what are your thoughts and what is the answer. Is it fine? You want to solve it, right, everyone? Please confirm if you get the problem. Anyone, please confirm if you get the problem. Am I audible? Hello. Please someone confirm if I'm audible. Hello. Okay, okay, yeah. So what I'm asking is you all should give it a try, right? You want to give it a try. Do you understand the problem? Okay, fine. Just take 2-3 minutes and let me know what approach are you following to solve this, and then I'll solve the same. This is quite a good problem. If you have understood all the concepts that I have already told in the class, then you will be able to solve it. And if you have any doubts in between, you can let me know there only.
Hello, sir. Hello.
Yeah, yeah,
Kindly repeat. Kindly repeat, sir. Probability of 2%.
yes.
What exactly is that?
Okay. So as I already told you that this particular function tells you the probability of electrons being filled at energy level E, right? I told you somewhere. Mm, yeah. So probability of finding an electron is Fe. So what I have given 2% is probability of finding an electron. Sorry. So you can say this is probability of being filled, and if I ask you that what is the probability of being empty or there is a hole, so it will be 1 minus Fe. So that is what I have given in the problem. I have said that the probability is 2% that the state 0.25 electron below the Fermi level will be empty. So the probability that I have given is for empty state, not the filled. So I'll let you know that this is nothing but 1 minus Fe, not Fe. Do you understand?
Yes, sir.
Yeah, just go ahead then. Yes, is there any doubt? Sanjeev, you have raised your hand. Is there any doubt?
No, sir. Mystically.
Yeah, sure, sure. Okay, so let me add one more thing. The value of K Boltzmann constant in electron volt is 8.62 times 10 raised to power minus 5 electron volt per Kelvin. You will require this, and it is, for your information, in joules it is this, but in this question you will require this. Anyone can share the approach that they are following, otherwise I'll solve it like right now. Anyone wants to share the approach that they are following? Okay, so let me try to give it a go then. So what I have already told that the probability, let's say the energy is E1 is 2% to be filled. So that is why I have written 1 minus Fe. And we have already solved that if I write 1 over 1 plus exponential E1 minus EF over KT. And if I solve and take the denominator and numerator, etc. So what I'll get is 1 over 1 plus exponential EF minus E1 over KT. That is given out by 2%, that is 2 by 100. So now the question says that I already have my what is the probability? So I already have my EF minus E1 as 0.25, and that is in electron volts. So what I can write here is if this is nothing but 1 by 50, 50 comes in the LHS, then this will be 1 plus exponential of 0.25 electron volts over kT, which will give me 49, and if I take the log both sides is 0.25 over kT. The temperature will come out to be 0.25 divided by ln 49 times k, which is 8.62, that is already given in the question. So this will be the answer in Kelvin. Is there any doubt in this? Did you get the approach? Please let me know if you are getting confused. I'll let you know again quickly. Is that fine, everyone? So on solving this will come out to be some 45.21 Kelvin. So I hope it is clear. So further, what are we interested in to calculate the carrier density? So what we are most interested in to calculate the number of electrons, that is the density of electrons that we have from the density of states. So which is getting which generally gets calculated by using the integral of the Fermi function that we read, the density of states that we read over some energy integral. And you already know about all of these formulas, so I'll not go into deep and just write directly the formulas that we have. So we have the energy is equals to NC exponential of EF minus EC over KT, or we have N equals to Ni exponential of EF minus EI over KT. Similarly, for holes, we have P is equals to NV exponential of EV minus EF over KT, and P is equals to Ni exponential of EI minus EF over KT. Like this is the guide for the basic formulas for the carrier concentrations, where N is for the electrons and P is for the holes. You already know these formulas, right? Please someone confirm quickly. Can someone please confirm? Please try to be interactive. That will help you more in getting the content of this course, because this might be new to you if you are a second year student. So try to be interactive. That will help, because this is a very important course if you want to have a career in semiconductors ahead. So please let me know if all of you have already read about these formulas. Anyone? Kindly respond. Have you seen these formulas before? Please at least type in the chat box. Yeah, sure. So you can try out this question then. You can take 5 minutes. So what we have is we have an intrinsic silicon. We already talked about what is intrinsic silicon. Intrinsic silicon means that it is pure silicon. That is, it is not doped. So the electrons and holes will be equal. That will be equal to the intrinsic carrier concentration, which is given in the question. So it is asking what is the Fermi level position related to the conduction band. That is, it is asking about Fermi level related to the conduction band. EF minus EC, and NC is also given, and you need to just find out this EF minus EC. So we have all the formulas. So just go ahead and let me know what is the answer that you are getting. You can take 2-3 minutes. This is very easy. If you have any doubts initially only, you can ask. I'll solve it. Otherwise, you should give it a go. Is it fine? And please respond quickly this time if this is fine, if you want to try. Just write yes in the chat box if you want to try quickly. Okay. Uh, is there any solution yet? Anyone? Maybe anyone can tell what they are trying. That will be great. So Shakshi, do you want to tell? What have you done? There is no language barrier. If you want to tell in Hindi, that is fine also. Anyone wants to tell what they have tried? At least let me know if you are still trying. Okay, so can you tell what did you do to get this 1.45? You can open your mic and tell. Anyone else who wants to tell? Okay, so let me uh, give you some idea and let me ask you to do one more question then. So what we have is we have an intrinsic semiconductor, we have a NC, and what we need to find is we need to find EF minus EC. So we have an intrinsic conductor that will give me N because that will be equals to Ni. We have Nc, we have Kt at room temperature, that is 25 milli electron volts. We just need to find this EF minus EC. So this is what we have to use in this particular formula. So we have N as Nc exponential of EF minus EC over Kt. N will be Ni because we have intrinsic silicon that is given as 10 raised per 10. Nc is given as 10 raised per 19 exponential of EF minus EC over kT, that is 0.025. I can write in milli electron volts. So if I do the division, basically I'm taking log both sides. So this will give me 1 over 3 10 raised to power 9. So EF minus EC will be, sorry, log of this 0.025 times log of 1 over 3 into 10 raised to power 9. Did you get what I did? Any doubts here? Anyone? At least write if you have any doubts or not. Any doubts here? Okay, so what do you have? Uh, do you have any doubts? You have written yes, sir. Okay. So if you solve this using the calculator, you will get 0.025 times then n value. Okay, fine. So we have our intrinsic silicon. Intrinsic silicon means we don't have any doping. So for intrinsic semiconductor, we have equal numbers of electrons and holes, and that is equals to the intrinsic concentration, which is given out in the question as 10 raised per 10. So that is what I have written. So I have written N as Ni. If let's say if this would have been a doped semiconductor, let's say P type or N type, so I would have written Nd. Okay, so give me blank page. So for intrinsic, N is equals to P is equals to Ni, and for extrinsic, we have now two types. For N type semiconductor, we have majority electrons, so N will be equals to approximately the doping concentration that we have. And for P type, P will be equals to the acceptor concentration that we have. So for the previous question, the case was that we have intrinsic semiconductor, so I've taken N is equals to P is equals to Ni. Do you understand? Okay. So if you solve this, you'll get this EF minus EC as minus, I guess, 0.56. And that will give you EC minus EF as positive value of 0.56. That makes, that is, what it is trying to tell is we have, let's say, EF. So EC is here. So this difference is 0.56. So the Fermi level is 0.56 below the conduction band. That is what is given in the option A. Do you understand? That is what we did for basic question also, that for an intrinsic semiconductor, we know that the Fermi level is between the EC and EV, and we already know that the difference is 1.12. So the half of that is 0.56. Everyone understood this question? Everyone please type in the chat box yes or no quickly. Everyone please write. And those who have understood the question, they can try out this. This is a exact similar question. In this we have the doping. So now we have the same with the N-type silicon. And I have already told you the criteria, which is this. Let me bring this. Fine. So you can try out this. I'll write for intrinsic again. We have NSPs as Ni. For extrinsic, we have N as Nd. If it is an N-type silicon, then for P-type, we have P as Na. Quickly confirm if all of you are trying and write yes in the chat box. Uh, See, we cannot waste time like that. If you should write in the chat box. I'm requesting everyone to write in the chat box. Please write yes or no if you are trying. Fine. Anyone tried? Any solution that you get? See, this time this is simple mathematics, so you should get some answer. I'm expecting some answers at least. Uh, did you get any answers? Anyone? Please type in the chat box whatever is the status. Yes, I've got one answer, which is option C. Anyone else with any answer? Okay, so Sakshi, I'd like to give you a hint that this is EC, this is EV, and this is EI. Uh, so what you are saying is you are getting the Fermi level above the conduction band. So just think through it, and at the same time, I'll try to solve it. This is again the same problem. We have n as nc exponential of EF minus EC over KT. N is given as ND because this is a n-type silicon. So I'll write the value. This is 3 times 10 raised to 17. NC is 3 times 10 raised to 19. And exponential of EF minus EC over 25 milli electron volts. So this will be nothing but 100. I'll get EF minus EC as, so this will be 100, 0.025 times ln 1 by 100, so that will be minus. So I'll get EC minus EF as 0.025 times 2.303, something like that. Not sure about the value. So this will come out to be 0.15 electron volts, which indicates that if this is the band diagram, this is Fermi level, this is EI. So EF is coming somewhere here, and the difference is 0.15. So EF is 0.15 electron volts below the conduction band EC. This is the answer. So what have you noticed is for an n-type semiconductor, the Fermi level is always close to the conduction band. And one more thing is for a p-type semiconductor, let's say this is the Fermi level, the Fermi level is always close to the valence band. This is what the conclusion for this particular question is, that for n-type semiconductor we will always have the Fermi level close to the conduction band, and for p-type we'll have the Fermi level close to the valence band. So for this question, EF is below the EC, which is around 0.15 electron volts. So that is option D. Is it clear to everyone? Please let me know if it is clear. Please try to interact. I'm asking everyone to type in the chat box if it is clear. Uh, is it clear? If you are not writing anything, that means it is not clear. So you can ask your doubts. See, I can solve this again and again. Please try to interact. Please try to type in the chat box. I've requested several times now. These sessions, live sessions, are for your problem solving. Please write yes if it is clear. Am I audible, everyone? Hello, am I audible? Hello. Okay, so since you are not responding, that is very bad. Let me try to give you one more question. So again, you need to determine the positions of Fermi level. I have a N-type silicon at room temperature. The Ni that you need to take is 1.5 10 raised per 10 per centimeter cube, and the doping level that we have is 10 raised per 16 per centimeter cube. And this time you need to calculate not EC minus EF, but EF minus EI. So this is the question. So you already have two formulas. Let me rewrite so that it will be easy. This is the first and this is the second. Please let me know right now if you really want to do it. Otherwise, I'll solve it. There is no meaning of wasting the time. Just write quickly yes if you want to solve it. Okay. So I'm not getting the response, so I'll solve it then. So we need to calculate EF minus EI this time. So we'll use this formula. So if I can write EF minus EI directly, This will be KT ln N over Ni, which will be KT ln Nd over Ni, because this is a N-type silicon. So we already have all the values. So we have 0.025 as KT. Nd is given out as 2 into 10 raised to power 16. Ni is given as 1.5 times 10 raised to power 10. So this is what we need to calculate. And you will get EF minus EI from this as 0.365 electron volts. That means if EI is here, then the Fermi level is somewhere here, and this EF minus EI is 0.365 electron volts. Does it make sense? Is it clear? Please respond. Do you want more similar questions? Please let me know. Do you want to solve, everyone? Do you want to solve a similar question again by yourself? So we have n number of questions in your assignments that are given to you this time. So I guess this is one of the problems. I'll go to this directly. Yeah. So do you want to solve it? Please write in the chat box quickly. See, I cannot just wait for your typing every time. I'll stop asking from the next time and just solve the problems. That will be no benefit if you're not understanding them. So please type in the chat box. Do you want to solve it? Am I audible clearly? Hello, am I audible? So please let me know, all of you, do you want to solve this? I'm talking to everyone. Okay, so I'll not ask again. I'll just solve the problems by my own. So in this question again, we have a n-type silicon since the electron density is given. So this is nothing but Nd. Then we have a semiconductor in which EC minus EF is given out by 200 milli electron volts, that is nothing but zero point 0.2 electron volts. So now the question says that we have again this KT is given as 26 millivolts, KT by Q, and we have an intrinsic carrier concentration Ni of 10 raised to power 10. So now it is asking that let's say we have a N of 0.5 into 10 raised to power 16, then what will be EC minus EF? So this is very easy. So for the first semiconductor, N is equals to uh, EC minus EV. So we have N equals to NC exponential EF minus EC over KT. So let's say for first semiconductor, I am denoting everything with N1, NC1, and this is EF1 minus EC1. And the second conductor that we will have the same NC2 exponential of EF2 minus EC2 over KT. So since we have that there is no temperature difference, so NC1 will be equals to NC2 for both the semiconductors. So what I'll do is I'll divide the first equation by second equation. So I'll get N1 over N2 as exponential of EF1 minus EC1 over EF2 minus EC2. If I take log both sides, so I'll have EF1 minus EC1 upon EF2 minus EC2 as ln N1 over N2. So I have everything that is given in the question. For N1 we have 10 raised to power 16. For N2 we have 0.5 10 raised to power 16. And for N1 we know that the difference is EC minus EF is 200 millivolts. So it will be minus zero point 0.2 divided by, or I can write it as plus, and I can just change the denominator EC minus EF2. This will be ln2. So EC minus EF2, which is as in the question, it will be nothing but 0 0.2, which is given, times ln2. That is 0 0.2 times 2 point, forget the value, I guess. So the question has asked it in milli electron volts. So on solving, this will come out to be uh, 218 milli electron volts. So this will be the answer. So let's move ahead. So now some of the questions from this year's assignment. It is saying choose the correct statement. So it says in a doped semiconductor, the ionized dopants, the acceptors and dopants. So doped means extrinsic. In extrinsic, we have, let's say for N type, we have Nd. For P type, we have Na. We have already seen that. So these are the fixed ionized atoms, or you can say ionized dopants, or they are immobile. They do not move at all. Can move freely. So this is the wrong statement. They cannot move freely. But in a doped semiconductor, the ionized dopant, that is Nd and Na, do not directly contribute. So they do not directly contribute because the main current flows due to the flow of electrons and holes, that is Nx and Px. So this statement is correct. So for this particular question, we have second is correct. Moving ahead. So we have the electron concentration given in asked in the question n in a piece of silicon maintained at 300 Kelvin at equilibrium. Okay, so n is given, sorry, as 10 raised to power 5 per centimeter cube. We need to find the whole concentration, and Ni is given as 10 raised to power 10 per centimeter cube. So we know that at thermal equilibrium, N times P is nothing but Ni square. So this will give me N is given 10 raised to power 5 times P is Ni square. So 10 raised to power 10 whole square. So this will give me P as 10 raised to power 20 divided by 5, 10 raised to power 15 per centimeter cube. So the whole concentration will be 10 raised to power 15 per centimeter cube. This is the answer. Moving forward, so we have a silicon which is doped with boron. So boron is a p-type impurity. So this is a p-type silicon having a concentration. So for p-type we have Na 10 raised to power 15 per centimeter cube. We have Ni given in the question as 1.5 times 10 raised to power 10 per centimeter cube. Vt again, that is Kt also. It is given as 26 milli electron volts. So compared to undoped silicon, the Fermi level is. So basically, you need to find out Ei minus Ef. You want to solve the same? You can write quickly in the chat box. Please type in the chat box. Yes, I'll give some idea by myself. So we have P as Ni exponential of Ei minus Ef over Kt. P is nothing but Na exponential of Ei minus Ef over Kt. N is given in the question as 4 10 raised to power 15. Ni is 1.5 10 raised to power 10 exponential of, since it is at room temperature, so we need to find this Ef minus Ei over Kt. So this will be Kt ln 4 into 10 raised to power 5 15 divided by 1.5 10 raised to power 10. So Ei minus Ef will be 0.025 or 6, whatever is given in the question, ln 4 divided by 1.5 into 10 raised to power 5. So it will be, I guess it will come out to be 0.325 electron volts towards the valence band. Any doubts? So there is a question in between that we have already done. This is again, I guess, given. So you need to tell me which temperature is higher, T1 or T2. We have already solved this, so let me know the which option is correct. You can type in the chat box your answers. We have already solved it in the initial part of the lecture. Any answers? Hello, am I audible? Hello, please confirm if I'm audible. I lost my connection, I guess. Am I audible, everyone? Hello, please quickly confirm if I'm audible. We are running out of time. Can you hear me? Okay. So we have already covered that higher the temperature, we will have a higher probability above EF to have the electron. So T2 will be higher in this case. So option B is correct. Then I guess there are a few more questions from this week's assignment. So we have this question in which the question says that we have a piece of silicon which is doped uniformly with phosphorus So phosphorus, it is n-type impurity. So we can write Nd as 10 raised power 16, which is given in the question. The expected value of the mobility versus doping concentration. So we have this mobility versus doping concentration plot given in the question itself. And the charge of the electron, so Q value is this. So what we need to find is the conductivity. So conductivity is nothing but sigma, which is equals to 1 by resistivity. And conductivity of any n-type silicon is given by nq mu, where n is Nd, that is the doping concentration. Q is the charge, that is 1.6 times 10 raised to power minus 19 coulomb, and mu is the mobility. So we need to find it at 10 raised to power 16, and this is the n-type impurity. So you can see in the plot that this is the point which is we have at 10 raised to power 16, and the corresponding mobility for the electron in this question is 1200. So you will use the mobility as 1200 centimeter square per volt second and solve the same. So we have everything. So conductivity is nq mu. So if I write n, which is given as 10 raised per 16, then we have charge as 1.6 10 raised per minus 19 and mobility as 1200. Everything is in centimeters. So this is 10 raised per minus 3. This is minus 1. So it will be 1.6 times 1.2, and it is asking in Simon per centimeter only. So this is the answer then, 1.92 Simon per centimeter. Sorry. So the answer will be 1.92. And then we have, okay, so we have a donor concentration. Again, we have a n-type silicon. So that means n is Nd. So it is increased by a factor of 10. So if it is Nd1 before, it is now 100 times of Nd1. So let's say this is Nd2. So assume the sample to be non-degenerate. So non-degenerate means that the Fermi level will be below the conduction band. So it is asking the shift if we change the doping concentration by 100 times. So this is nothing. So the change will be very easy. Again, we'll divide the same things and we'll get the change. So it will be nothing but KT, which is given as 25 millivolts, divided by Nd2 minus Nd1. So this is what we'll get, 0.025 ln 100. This will be 0.025 into 2 into 2.303. Yes, which will come around 0.1155. It is asking in milli electron volts, so it will be 115.5 milli electron volts. So this will be the answers. So these are some of the basics question that we have covered regarding the band diagrams and the Fermi levels and the carrier concentration. So if I quickly go to the course outline, so we have covered almost all the topics of the week 2. So if you get the idea of the week 2, if you don't get the idea, please try to see the video that will be uploaded on the YouTube channel again, because you need to get the idea to get the like all the other topics will be tough to you to capture if you don't have the idea of the this lecture, because again we'll go into the electric field and the current components of the PN junctions and other devices. So please try to see the YouTube video before coming to the next lecture if you don't get the idea. So please let me know if you have any query. Otherwise, we can wrap up this session for today. Is there any query? Anyone? Okay, then thank you for attending the lecture. We can wrap up this session and we'll meet us next week, same time to cover the topics for week 3. Thank you for joining, everyone.